Hi, and welcome to the November 2012 Namibian Higher Level Paper 2 videos. Okay, so we're starting at question 1, and again, just like with paper 1, we'll be doing one question per video. So we're starting at question 1. Again, it is given that we get given a function. Let me just write that down in case it might be a little bit difficult to see. Not that my handwriting's any better, but we've got 3x cubed minus 8x squared minus 5x plus 6. Alright, so we're given that. Now question A says, show that x minus 3 is a factor of fx. Okay, to show if something is a factor, the remainder theorem states that if we do f of some value, let's say f of a, if the answer to that is 0, this is the remainder, right? So if the remainder is 0, then something is a factor. Alright. So that's the basic idea. Hopefully that makes sense. So what we're going to do is we must show that x minus 3 is a factor. So to find out what x must be, then we'll put this equal to 0 and solve for x. So we see that if x must be 3. So what we're going to do is we're going to plug in 3 into our equation, and if we get 0 as an answer, then we've proven that x minus 3 is a factor. Okay, so we just plug that in. So 3 times 3 cubed minus 8 times 3 squared minus 5 times 3 plus 6. Okay, so this gives us 27 times 3 is 81. 9 times negative 8 is negative 72. Negative 5 times 3 is negative 15. And then we add the 6. Okay, so let's do 81 plus 6. That gives us 87. Negative 72 minus 15 is negative 87. And we get 0 as an answer. So that is proven. Very nice, very easy. Okay, so let's just recap here quickly. Actually, let me do that. At the end of the video, I'll recap the remainder theorem, the basics behind that. For now, let's just continue with the question, for those of you who already know what the remainder theorem is. Question B, the polynomial can also be written as, and let me rewrite that again, x minus 3 in one bracket, and then another bracket containing ax squared plus bx plus c. Okay, now it looks like it didn't copy well. That should be bx plus c. Okay, and now they ask us, if it can be written like this, find the values of a and b and c. So a couple of ways we can do this. We can use this by doing long division, finding an answer and putting that equal to the normal way, finding the remainder. But what I'm going to do is I'm going to use equivalence. So I'm just going to multiply this out and then compare that answer to the original function. Okay, so let's multiply it out. X times ax squared gives us ax cubed, and then multiply it to the second one. So x times bx is bx squared, x times c is cx. Then we do the next value. So negative 3 times everything. Negative 3 times ax squared is negative 3ax squared. Negative 3 times bx is negative 3bx, and negative 3 times c is negative 3c. Great. Now let's collect our like terms. So for all the x cubeds, there's just one term x cubed, so that's ax cubed. Then the x squareds, that'll be these two. So for the x squareds, we can factor out the x squared, and what's left is the b minus 3a x squared. And then for the x's, that'll be those ones. So there we can factor out a c minus 3b x. And then the negative 3c just remains at the end as a constant. Okay, so now what we want to do is we want to compare the x cubed, x squared, x, and constant terms to the original function. So let's compare the coefficients of the x cubeds. So we know it must be a must be equal to the coefficient of the x cubed in the other function. So a must be equal to 3. Nice, done. Then we do the x squareds. So for the x squareds, their coefficients must also be equal. So we've got for this one b minus 3a. So b minus 3a must be equal to negative 8. Negative 8. The nice thing is we already know what a is, so we can plug that in. So a is 3, and then we can just solve for b. So b minus 9 equals negative 8. Take over the negative 9, and we get b equals negative 8 plus 9 is 1. So now we know b. Then we can look at the x terms, x to the power 1s. So we see c minus 3b over here is the coefficient. C minus 3b, that must be equal to the coefficient of the original, which is negative 5, as we can see there. Okay, so equals negative 5. Now again, bonus, we already know what b is, so we can plug that in. So c minus 3 times b equals negative 5. This gives us negative 3, and if we take it over, we get negative 5 plus 3, which is negative 2. And there we have it, A, B, and C. Fantastic. Question C, last one left. Question C, now this tells us just solve the equation, f of x equals 0. Okay, so now we already know f of x can be written as it is here. So I'm going to do that. I'm going to say we know f of x is x minus 3 times ax squared plus bx plus c. But we already know what ax, a, b, and c are. So a was 3, so ax squared becomes 3x squared. B is 1, so bx becomes 1x. And c is negative 2, so c becomes negative 2. And that's still equal to 0, so here we've got fx equals 0. Now we can factorize this part a little further. We'll keep the x minus 3 in the front, that's already fine. Now this we can factorize even more. And if it couldn't factorize, then we could just plug this into our quadratic formula or use completing the square to solve for x for that part. But this one can factorize, and I think it looks like it'll be 3x and x with a plus 1 and a minus 2 over there. That seems to work. Okay, now we've got 3 brackets, and this times this must be 0, which means either this must be 0 or this bracket must be 0, or the last bracket must be 0. And then we can just solve each one separately. So here we just take the negative 3 over and we get x equals 3. Or here we can take, I forgot to put the equals 0 part. Here we take over the 2 and then divide by 3, so we get x equals 2 over 3. Or lastly, here we take over the 1 and it becomes x equals negative 1. And that is it for question 1. Now let's just go back to the remainder theorem briefly. So the remainder theorem, and I'm just going to explain this not formally, just sort of the idea that we often use to answer kind of questions like this, like question A. So the remainder theorem just says that if we divide something by something else and the remainder is 0, then we know that thing was a factor. Let me give you a concrete example with some integers. If we say 7 divided by 2, what does that give us? Well, that 2 can go into 7 3 times, and then there's a remainder of 1, right? Because 2 times 3 is 6, so we still need to add 1. So that means the remainder is not 0, so that means 2 is not a factor of 7. On the other hand, let's say if we take 6 divided by 2, what does that give us? 3, and there's no remainder. The remainder is 0. So that means 2 is a factor of 6. Now exactly the same here. What we did was we said if we take f of x and we divide it by x minus 3, then we get something with a remainder of 0. Right, so if we got a remainder of 0, then we knew that that is a factor. So that's all we did, we just found the remainder. And now the theorem says that if we have some function, and let's say like this, if we, okay, I'm going to do it below here. If we take f of x and we divide it by some linear factor x minus a, right, then the remainder we'll get can be found by saying, how will I do this? The remainder we can find by saying f of a, right? So f of a equals the remainder. Perfect, so that's all we did. So that's in our case we had f of x divided by x minus 3. So that means to find the remainder we said f of 3, right? So f of a gives us the remainder. In this case f of 3 will give us the remainder. We found f of 3 was equal to 0, so the remainder was 0, which means this is a factor of that. If you have a remainder of 0, you have a factor. Alright, I hope that helped a little bit. It was not a formal explanation or a very deep and good one, just a cursory look at how we can use that to find factors. Alright, and then I'll be back shortly with question 2.